Happy Monday. Let's start out with a discussion of the plan for the week. So today we're going to be continuing our discussion on elastic potential energy. We're going to be applying what we talked about to graphs. Tomorrow, Tuesday, we're going to take our understanding and take a look at a real-life system using a simulation. On Wednesday, we will have another mandatory Google Meet, in which counts as a participation grade. You must attend and participate, meaning answer the question in the Google chat or play Kahoot or any other review game that we engage in. If you show up and you participate, you get the 10 points. If you know for a fact that you cannot attend before the meeting, you can send me an email and let me know. If an emergency occurs, like you lost power, and you cannot attend the Google Meet, you need to let me know as soon as possible so that we can talk about a way to address those points. If you have any questions regarding those meetings, please let me know. On Thursday, we'll begin our review and discussion of simple harmonic motion and the assessment. On Friday, we'll begin working on the assessment. Again, a warning, this assessment will look differently than our previous assessments. We'll talk about how it will be graded and the options that you have when we get there. All right, so let's start out today, this morning, with a do now. So this do now is a little bit trickier than the two problems that we looked at on Friday. But what I want you to do is pause the video and give it a try. Given and what we know. So we're told that it takes 20 newtons of force to hold a spring at a displacement x of 40 centimeters. We know that the units that we need here have to be meters in order to find K in newtons per meter. So x is going to be 0.2 meters. 0.4 meters, excuse me. As it's stretched to a distance of 40 centimeters. So x is going to be 0.4 meters. We want the elastic potential energy, U sub s, stored in the spring. We know from class on Friday that elastic potential energy, the energy stored in a spring's position, is equal to 1/2 times the spring constant times the displacement of that spring squared. So it can either be a stretch or compression distance. We have the stretch distance. We don't have the spring constant. So how could we find the spring constant, K? What other relationships do we know of that contain that variable? Well, hopefully we're thinking Hooke's law, right? So in order to find K, if we know the force and the displacement, which according to Hooke's law for a spring, an ideal spring, they're proportional, we can use Hooke's law, which states that the restoring force, F sub s, is equal to negative K times the displacement or stretch of the spring. So I'm going to take my values and plug in. Okay, we know that force and displacement have to be in opposite directions. So up to you which one you want to make negative. Doesn't technically matter. In this situation, if we pretend this is a vertical spring like those that we've been looking at, technically the displacement would be below equilibrium. So we're going to make x negative. You could, though, however, visualize this as a horizontal spring mass system because it doesn't specify in the problem. And you could assume that this x would be positive, meaning to the right. Regardless of which way you're picturing or visualizing this, you will get the correct value for K. That is why they don't give you an image or an exact description, because it does not affect the spring constant of the spring. So I'm going to decide to make K negative instead of force negative. Regardless, again, they must have opposite signs. So my last step is to divide both sides by that stretch distance to find K. Which we now know is 50 newtons per meter. Now that we have our K value, our value for a spring constant, we can now go back and plug into our relationship for elastic potential energy and find the energy stored in the spring at that position. So let's go ahead and do that. So again, we know that our relationship for elastic potential energy, we just found our K value, so we can now plug in for that. And the displacement remains the same. So first step, right, order of operations, you must square 0.4 first. 0.4 squared, we get 0.16 meters squared. We see that one of our meters cancel out here, and we can multiply straight across. So I'm going to take 0.16 times 50 times 0.5. We get 4. These units here, we're left with newtons times meters. So let's take a look at these units a little bit more closely. So technically here, we have Newton times meter. We know a Newton is equal to a kilogram times meter over a second squared. We are then multiplying that definition, or that set of units, by meters. So we get kilograms times meters squared over seconds squared, which is actually the definition of a joule. So what we have here, through dimensional analysis, is joules, which is exactly what we'd expect, so we know that we did the algebra correctly, because our units check out. So the energy stored in the spring due to its position would be 4 joules of energy. And again, that energy can be converted usually to kinetic energy, but other types of energy as well. Okay, awesome. So this example kind of brings it all together. So we have Hooke's law and elastic potential energy working together as a system to find more information about that system. What we're going to talk about next is how our results from our lab tie in to what we discussed on Friday. So we know from lab see if I get this to work. of a spring. An ideal spring. Graph the force versus stretch of a spring. An ideal spring. What's going on here? I'm just going to write an X in here to save us some time because this is not working out too well. There we go. So we graphed the force versus stretch. We determined that we found a linear trend line. And the slope of that trend line was our force divided by our stretch, in which we define as a spring constant. So we can actually find that spring constant graphically. We can also use this graph, the force versus stretch graph, for an ideal system, meaning that it follows Hooke's law. We can use that graph to find the elastic potential energy. And how we do that is we would take the area underneath our curve. Okay, so this area here will give us our elastic potential energy. Let's demonstrate. So the area of this graph, you can see here that this is a triangle. The area of a triangle is 1/2 the base times the height. Our base would technically be our X value, our stretch value, and the height would be our restoring force. Dimensionally, we will get the correct units. Okay. So let's actually give this a try with some numerical values. That way it makes a little bit more sense. Okay, so this is a sample graph from an ideal spring mass system. So we see that our force increases at a proportional rate. Technically, our stretch here is in centimeters. We're going to modify that to be meters. So as you're sketching this in your notebook, you have force in newtons and stretch in meters. Some point values we have 0, 0 as our y-intercept, 1, 1, some other good points. Let's see. This one's pretty accurate. Hopefully we can see those dots there. So 5.5, 5, 8.5, 7.5, and 10.9. Okay, and then we want a best fit line there. We're going to take the area underneath that curve. So we know that the elastic potential energy will be equal to the area underneath a force versus stretch graph. Again, this shape here, if we draw a line with the x-axis, we have a right triangle. To find the area of the right triangle, we take 1/2 times the base times the height. Our base is 10 meters. And our height is 9 newtons. So when we multiply straight across, we have 1/2 of 90, which is 45. Our units are Newton times meters, which we just showed in our previous example is equivalent to a joule. So our elastic potential energy stored in the spring due to its position, assuming that stretch was in meters, would be 45 joules. We can actually double check this. Can anyone think of another way in which we could determine the elastic potential energy stored here? Well, technically, right, we know that m, our slope, is equal to the spring constant. So we could take the slope here between any 2 points on the trend line and then plug that in. X value, square it to find u sub s, and we will get the same exact value, 45 joules. As long as the points that we choose are on the trend line.